Thank you for joining us tonight for this presentation by Professor Mark Jacobson. Mark was scheduled to speak at a laser Leonardo Art Science Evening Rendezvous, a series that I started in 2008 and that is on hold during the pandemic. If you are familiar with the laser program, if you're not familiar with the laser program, check lasertalks.com. If you are familiar with it, you can find the calendar there of these online talks. We replaced the physical laser of June 2020 with online presentations, and tonight it's Mark's turn. Next will be Andra Key of the Silicon Valley Robotics Association on June 15. She will speak on robotics and pandemics. Without further ado, Mark Jacobson is Professor of Civil and Environmental Engineering and Director of the Atmosphere Energy Program at Stanford University. If you registered for this event, you already saw the long version of his biography, so I will not repeat it here. Mark, please share the screen, and I'll turn off my video to minimize bandwidth. Yours.
Thank you, Piero. So today I'm going to talk about transitioning cities, states, countries, and the world to 100% clean renewable energy and storage for all energy purposes. And the reason I want to look at this issue is not only to try to address global warming, but also to try to eliminate air pollution problems, because air pollution kills 7 million people per year worldwide and injures hundreds of millions more. And third, we want to address energy security and energy poverty. So the plans that I'm going to discuss, they will not only plan out a path or provide a path to transition countries and cities and states, but these plans are basically Green New Deal plans for each of these countries and cities and states, where a Green New Deal is really a method to transition all the way to 100% renewable energy for all these locations. So the idea behind these plans is to electrify everything. Biofuels or nuclear power for that matter. Even though biofuels, for example, are renewable, they create air pollution. So we don't include biofuels, biomass, bioenergy of any type. We don't include nuclear power, even though it has low carbon, it still takes energy to refine uranium. And that energy has to come from somewhere, and often right now from fossil fuels. But there's risks associated with it, including meltdown risk, waste issues, nuclear weapons proliferation risk, and mining risks, and their high cost and long delays due to reactors. So it's pretty much impossible even to put up a reactor between planning and operation of less than 15 years right now. So anyway, our plans are to electrify everything. And by electrifying everything, we mean like not only transportation, but heating and cooling and industrial processes. And we'll provide that electricity with clean renewable energy. So for example, for transportation, we'd use battery electric and hydrogen fuel cell vehicles. Hydrogen fuel cell will be for long distance heavy transport. Battery electrics will be pretty much everything else. So long distance heavy transport means long distance ships, long distance aircraft like 747s, we'd transition those to hydrogen fuel cell. But short haul flights, we'd all be battery electric. For heating, cooling, for building heating and cooling, we'd use electric heat pumps, which use like 1/4 the energy as a natural gas heater or even electric resistance heater. And that would be also used for air conditioning and water heating. We'd also use solar hot water preheating, some direct geothermal heat, and we'd also use district heating so that we can have these centralized heating and cooling systems that will distribute the heat and cold to buildings through pipes. For high temperature industrial processes, instead of burning oil, gas, or coal, we would use electric arc furnaces, induction furnaces, resistance furnaces, dielectric heaters, some electron beam heaters. These all run on electricity, and they're all existing technologies. In fact, about 95% of all the technologies we need are already existing. The main exceptions are these long-distance aircraft and long-distance ships, which haven't been transitioned yet. And for all the electricity that we'll use, we'll provide that electricity and heat, in fact, with onshore and offshore wind, solar photovoltaics on rooftops and in power plants, concentrated solar power, geothermal power, existing hydroelectric power, like conventional dams that are existing, and tidal and wave power. And the hydro we'd use primarily for balancing, for trying to meet peaks in demand when we don't have enough wind or solar, and because it's very fast as a backup source. Now, just to give you some ideas of some of the technologies for onshore and offshore wind, well, onshore wind and utility scale solar PV are now the two cheapest forms of electricity in most places worldwide. And they're, some places they're half the cost of natural gas. And onshore wind can be put up, in any location where there's not only fast winds, but you can put it on farmland or agricultural land, range land, places where there's open space. So it doesn't take up a lot of space, but you do need spacing between wind turbines that you can use for multiple purposes. Now, offshore wind is growing fast, particularly, and we expect it to grow even faster now with the onset of commercialized floating wind turbines. And this allows, because there's so much offshore wind resource worldwide that's uncaptured right now, and we only need a small fraction of that to power most of the world. And the advantage of these floating offshore devices is that you can put them far out so people don't see them. And in some places, like the west coast of North America, where the water depth goes down very quickly, gets deep pretty quick, you need floating wind, offshore wind to, otherwise people will complain. Now, on the east coast of North America, it's pretty shallow, so you can put offshore wind into the sea floor out to great distance, but still floating will have an advantage. Now, solar photovoltaics, you can not only put on rooftops and in the desert or in large-scale power plants on land, but you can also put them over water. And this is really important because there are a lot of locations that are land constrained, and the only place you can put solar, if you want to do this on a large scale, is over lakes and reservoirs, and even over the ocean if you put like a breakwater. Now, there's advantage of putting solar on top of a canal or reservoir because it reduces evaporation, and so that actually has dual benefit of saving water for water supply. Now, for transportation, there have been great advantages, great strides in electrifying even trucks. So, for example, this on the top left is a Tesla Semi, which is an electric version. It's all pure electric. It goes 850 kilometers. On the top right is a hydrogen fuel cell semi that's hydrogen fuel cell powered, and it's by Nikola, but it goes up to 1,200 kilometers. So as I mentioned before, for long distance heavy transport, we'll probably use hydrogen fuel cell. For short and moderate distance, pure electric. Because problem with trying to go long distance with pure electric is you'll just need more batteries to carry around the batteries. Whereas hydrogen, you can add, you can refuel it, the hydrogen, faster right now, unless you can do battery swapping, which is also possible, but hasn't been done on a large scale yet. But for hydrogen, you can either refuel it faster, or you can have larger storage tanks that don't require so much mass. Now, there are also electric ferries available. On the bottom left is an example of an electric ferry that exists now in Norway. And there are hundreds of thousands of electric buses available on the road. And most of these are actually in China right now. There are at least 500,000 in China, but there are also in many countries of the world, there are now electric buses. So those are becoming widespread. For aircraft, there are prototypes of electric aircraft, like on the left by Ampere, and there's a hydrogen fuel cell aircraft that seats 4 on the bottom right, and it goes 1,500 kilometers. But so far, there's still not an existing 747 type aircraft that's been converted to hydrogen fuel cell. On the top right is a drawing of a cryogenic, which is hydrogen aircraft. And cryogenic just means that the hydrogen has temperature is low and it's compressed into liquefied compressed form. And so it's less dense, or sorry, it's more dense and lower volume when you do that. Now, we'll need storage to transition, and electricity storage, heat and cold storage, and also hydrogen storage. So the types of electricity storage that are available today are concentrated solar power with storage, pumped hydroelectric power, existing hydroelectric dams, batteries, flywheels, and compressed air storage and gravitational storage. And I'll show you some examples of these. In heating and cooling, there is water tank storage, ice storage, and then underground storage in boreholes, water pits, and aquifers, and also in building materials. Now, the advantage of underground heat and cold storage is that you can store the heat or cold for months, like up to 6 months even, underground in boreholes or water pits, for example. And so that allows you to have seasonal energy storage. So for example, if you have a lot of sunshine in the summertime, you can then store the heat from the sunshine in water or in soil for 6 months until winter, when the snow is on the ground. And this is beneficial because in some places, like in the US, for example, there's a 4 times the heating demand in the winter is 4 times the cooling demand in the summer. So you do need a lot of heat stored in the winter. But let's say you have a 100% wind, water, solar system. Maybe in some locations there's not much wind and very little solar during the winter, and you need heat. And if you want to provide that heat from wind, water, solar, one way is to actually have it stored from the summertime and then use it in the summer. So I'll show some examples of some of these storage types here. This is gravitational storage with solid masses. It's a new technology, although it's very similar to pumped hydroelectric power. Pumped hydroelectric power is the most common type of storage of electricity in the world right now. Well, in addition to existing hydroelectric dams, which are also even larger in terms of their capacity. But the way this works is when you have wind and solar, when you have excess wind, because remember, the wind is intermittent, it doesn't always blow, but sometimes it blows a lot and you have too much wind. So if you have too much wind, you can use that excess to lift these blocks up onto the top of this tower, and by use the electricity running through a motor to lift the blocks. But then a motor can run in reverse. When you need electricity, it can run in reverse as a generator by just lowering the blocks. And you turn a wheel, and that wheel runs the generator and to produce electricity. The same idea is in these, on the right, you have these trains that contain either rocks or concrete blocks. And when you have excess electricity, you push the train up the hill. When you need the electricity, you let the train roll down the hill. And so the efficiencies of these are pretty high, around 82%. They're similar to pumped hydroelectric power, but they haven't been, well, they exist and they're starting to be commercialized, but they haven't been fully commercialized yet. So we don't know exactly what their cost is, but it's expected to be relatively similar to pumped hydroelectric. Now, another type of, this is a district heating system, storage system. It's actually at Stanford University where I work, and it's called a 4th generation district heating system, because it not only includes heating, but it also includes cooling. And there are 2 cold water tanks and a hot water tank. And this was, well, until 2016, Stanford was powered 80% by a natural gas cogeneration plant that provided 80% of both the electricity and heat for the campus. And then in 2016, it was replaced with this district heating system. And the district heating system, it's connected by pipes to all the buildings on campus. And so the heating, hot and cold water and air are provided by this heating and cooling system and the pipes. And the heat is provided with heat pumps, and the cold is provided with heat pumps. And not the source of the heat or the cold is waste heat from, like, because when you produce cold, you have waste heat, and when you produce heat, you have waste cold. And if you capture that waste heat and cold and then put it in the cold and hot water tanks, then it's more efficient. But the heat pumps are run on electricity, so the university also purchased about 120 megawatts of solar photovoltaics. There's 10 megawatts on rooftops, and the rest are in 2 big power plants that were built. And the second one is being completed now. And when it's finished, maybe at the end of this year or next year, the campus will be 100% renewable, not only for electricity, but also for heating and cooling. So it will be the first campus in the world to be 100% hot, cold, and electricity from renewable energy. So I think that's kind of cool. Now, here's another type of storage, which is the heat storage underground in boreholes. Now, this is a town in Okotoks, Canada, which is 1 hour south of Calgary. There were 52 homes built in 2004 and 5, and on the garages are these solar collectors that have a glycol solution. And during the summer, when the days are long, this glycol solution collects heat. The heat is transferred by pipe to this building on the right. And from the building, the heat is transferred to water in pipes. The water is then piped underground, where there are U-shaped pipes underground that, excuse me. A sec. Excuse me. There are U-shaped pipes underground that the heat from the water is transferred to the soil. It'll take me a second to recover here. Yeah, the heat from the water is transferred to the soil. The soil heats up to about 70 or 80 degrees Celsius. And the heat is stored in the soil for up to 6 months. Then during winter, when the snow is on the ground, the whole system is run in reverse, and the heat is transferred back to the water and cold pipes, and to heat up the water in the pipes. Then the heat is sent to the buildings, and that heat provides 100% of the wintertime heat for these 52 buildings. So the nice thing about this underground storage is it's very inexpensive. It's less than $1 per kilowatt hour of storage versus for batteries, for example, it's $200 to $300 per kilowatt hour. So this is an effective way of trying to provide heat to a community. Now this is similar, this is called water pit storage, where you have a big kind of swimming pool-like structure that holds water, and it's insulated on the top when it's filled. And these solar collectors will collect heat in the summer and send that heat to the water, and the water again gets up to 70 or 80 degrees Celsius, and the heat is stored until wintertime. And that provides, in this case, for this town of 2,000 or 3,000, that'll provide the wintertime heat for the town. So again, this is very inexpensive, less than $1 per kilowatt hour of storage. Now, here's another type of thermal energy storage. It's an ice. So ice storage works well. So at nighttime, actually Stanford had a big ice cube under a building like this starting in 1998. And at night, when the electricity price was low, the electricity was used to produce the ice. Then during the day, when cooling was needed, water was sent through coils in the ice and then piped to buildings, and then the buildings were kept cool. So this avoided air conditioning use, and air conditioning requires electricity. So it's basically electricity storage, but it's like 1/10 the cost of electricity storage. And ice is used a lot today in stadiums and hospitals as a mechanism of storing cold for use for air conditioning and other cooling. Now, I want to talk next about transitioning individual buildings, particularly homes. And I'm going to use an example, my own home, which I completed building in 2017, so 3 years ago. And there's no gas on the property. It runs entirely on solar PV. So, but it is connected to the grid. So when I say runs entirely, in the annual average, it produces about 120% of its annual electricity, but there are times when it needs electricity from the grid, but it sends more electricity back to the grid than it takes from the grid in the annual average. So there are 13.7 kilowatts of installed solar PV on the rooftops. There are 4 first-generation Tesla wall-mount batteries, although only 2 are used. So when the sun hits the panels first in the morning, the electricity is first used for home electricity use. What's left over is then sent to the batteries to fill the batteries every morning. And then if there's more after filling the batteries, the rest is sent to the grid and sold to the community choice aggregation utility that I have a contract with, who will purchase the electricity at the same price as I would have to pay for it. So this is really a good deal, and I'll show you some results in a few minutes. But And there are also, so there are electric cars, but for heating, I have heat pumps. So these are called ductless mini split heat pumps and air conditioner, heat pumps for heating and air conditioning. And there are two of these outside units on the right, which basically these outside units will take the air from the outside and try to extract either heat or cold from them. So the way heat pumps work is they move heat around or cold around rather than create heat or cold. So they use like 1/4 the energy as a natural gas or electric resistance heater. So for each outside unit, which I said there were two, there are about 6 inside units. So there's one inside unit in each room. And it's basically, it runs by having a fluid, a coolant tube that goes between this outside unit and the inside unit. And that coolant tube, so it's enclosed so the coolant doesn't leak to the air. But anyway, it's really efficient. These heat pumps are really efficient, and I really recommend installing them even if you have an existing gas heater, either for air or water, as I'll show. So here's my water heater, which is also a heat pump water heater. In this case, the heat is taken from the mechanical room that the water heater sits in. And so the mechanical room becomes slightly cooler, but only slightly, but the water gets really hot. And when the mechanical room gets slightly cooler, in the summer, you can just open the door of the mechanical room and that'll provide additional air conditioning for the house. In the winter, the temperature drops as well slightly in the room, and that would require slightly more heat pump air heating electricity to replace the heat that's moved to the water heater, but it's not very much. As I'll show you the overall power consumption in a second. For cooking, I have an electric induction cooktop, and these are much better than electric resistance stoves. They're more efficient than electric resistance stoves, but they boil water in half the time as natural gas does. The stove does not feel hot when you touch it because the way it works is you have to have a pot that has an iron or stainless steel base that has high resistance, and the electricity from the stove, it excites molecules in the pot and the resistance, and so the pot heats by resistive heating, and so the pot becomes hot, but it only conducts some heat to the stove, so the stove only becomes warm. And so if you touch the stove, you're not going to burn your hand. So that's the nice thing about these stoves. They're efficient, they cook evenly, and they boil water very quickly. Now, there's also LED lights, and the home is very well insulated. So I just finished 3 years of energy use in the home, and over that 3 years, I generated 120% of all the home and vehicle energy from the solar PV. Or I produced 120% of all the home and vehicle energy. In other words, 20%. I produced 20% more than I consumed, and I sent the rest back to the grid. I had no electric bill, gas bill, or gasoline bill for any of the 3 years, and I received an average of $700 per year back from the CCA for the excess electricity I sold. So this pays itself off, well, with subsidies, which there are in the US and in California. With subsidies, the payback time is about 5 years. Without subsidies, it would be about 10 years. So the numbers on the bottom left here are ranges for typical households, or ranges for most households. So you avoid, by having an all-electric home from the start, you avoid a gas hookup fee, because my underlying utility, which is PG&E, would have charged about $5,000 or $6,000 just to hook up gas to the property. So I did not have to pay that. I also avoided gas pipes, avoided an electric bill. The range for typical households is $1,000 to $3,000 per year. Natural gas bills, $1,000 to $3,000. Vehicle fuel bills, $1,000 to $4,000 per year. So the total savings is $4,000 to $15,000 up front, plus $3,000 to $10,000 per year. And anyway, it's net benefit. I advise everybody to do this. It's whether you have a new house or a retrofitted house. If you can't put solar on your roof, you can also directly, in the states that have CCAs, which there are 7 states in the US that have CCAs right now, you can directly contract with them. Well, they will contract 100% renewables, so they can actually purchase 100% renewable electricity and then sell you 100% renewable electricity at virtually the same price as your utility that doesn't have 100% renewable electricity. So that's the nice thing about CCAs is even if you're in an apartment complex and you have an apartment, for example, or you can't put solar on your own roof, you can still contract with the CCA and get 100% renewable. And so this, I would recommend this strongly. Okay, so then the next question is, can we transition the entire world to 100% clean renewable energy for everything? So we developed roadmaps for 143 countries of the world, and each roadmap is basically a plan to go to 100% renewables. And so this shows kind of the sum over all 143 countries of a few parameters. Well, one is the end-use demand for all energy in 2016, and that was 12.6 trillion watts or terawatts. And by the way, all these 143 countries, they represent about 99.7% of all global greenhouse gas emissions. Now, in 2050, the anticipated demand, end-use demand in all these countries is expected to be 20.3 trillion watts. But if we transition to wind, water, solar, it's expected to go down to 8.7 trillion watts, or a reduction of 57%. Now, of this 57%, 21.7% is due to the efficiency of battery electric. The 21.7% reduction is due to the efficiency of battery electric and hydrogen fuel cell vehicles versus internal combustion engine vehicles. For example, a battery electric vehicle, 80 to 86% of the electricity going into the car goes to move the car, and the rest is waste heat. Whereas a gasoline vehicle, only 17 to 20% of the energy in gasoline goes to move the car, and the rest is waste heat. So each battery electric vehicle uses about 1/4 the energy as a gasoline vehicle. But when you average over all energy sectors, there's a 21.7% efficiency reduction or improvement. Now, electrifying industry reduces energy demand 3.4%. Electrifying building heating and cooling reduces about 13% due to the efficiency of heat pumps. Eliminating fossil fuel mining, transporting, and refining eliminates about 12% of all energy worldwide, because that's how much energy is used to just mine, transport, and refine fossil fuels and uranium. And then 6.6% is due to end-use energy efficiency improvements beyond business as usual. So that adds up to 57% reduction of demand without really changing your habits. So that's very positive. That's a good result. Now this kind of shows the same thing. It's just but in a graphical sense. It shows how power demand is expected to rise between now and 2050, expected to go up to 20.3 terawatts, the same number I gave on the last graph, among these 143 countries. And then each of those shades of, you can see the decrease if we electrify everything, going down to that 100% WWS line of 8.7 terawatts, due to the same 5 reasons I just discussed. But then in 2050, we would power that 8.7 terawatts on average by a combination of onshore and offshore winds, solar, geothermal, hydroelectric, tidal, and wave power. Now, we propose that this transition, we need about 80% of this transition to occur in the next 10 years, or by 2030, and 100% no later than 2050. And the reason we need such a fast transition is that to avoid 1.5 degree global warming, we're already at 1.1 degree global warming, but to avoid 1.5 and to avoid most of the 7 million air pollution deaths per year that are occurring worldwide, we need to eliminate emissions as fast as possible. So we propose 80% by 2030, and we think that will do the job. However, we also need to address not only energy emissions, but non-energy emissions, such as reducing biomass burning, reducing like open biomass burning of rainforests and other types of forests, and also reducing emissions of methane from cows and from rice paddies and other sources of methane. Also reducing halogens that are used as coolants, we need to eliminate emissions of halogens, because when they're being used, halogens don't cause a problem when they're actually being used, but it's just when they're at the end of their life or if they leak, that's when they start causing problems. And because halogens cause about almost 10% of global warming. So we need to eliminate emissions of those. So in terms of global warming, energy is about 70% of global warming, but in terms of health, it's about 90%. So our plans deal primarily with energy, but we also propose that we address non-energy emissions as well that will affect climate. but we do need 80% of everything done by 2030. And this is a tough job, but it can be done technically and economically. Now, averaged over the 143 countries, we propose that about 30.5% of our end-use demand will be supplied by wind, or onshore wind, 14.5% by offshore wind, 11% by residential rooftop PV, 14% commercial government PV, 19% solar PV power plants, 4% CSP, 1% geothermal, 6% hydro, which exists already. Those are existing, that's existing hydro, and less than 1% tidal and wave power. So how much land would this take up? Well, we don't need land for tidal and wave or offshore wind or rooftop PV. We're not adding any new hydro, and there's hardly any new geothermal. So the main new land is onshore wind and utility PV plus CSP. Now the wind is mostly spaced between turbines. So in fact, a lot of that PV, utility PV, can actually go on the same land as the wind. And so so the total here is 0.65%. But if you overlap utility PV with some of the wind, you'll get less than 0.65%. Now in the US, that number is closer to like 0.9%. So less than 1% of the land. But keep in mind that 1.3% of all US land right now is used for the fossil fuel industry. That's the 1.7 million active oil and gas wells, 2.3 million inactive ones. There's 50,000 new oil and gas wells every year. There's millions of miles of pipeline. There's storage facilities, there are refineries, there are coal mines, you name it, gas stations. There's all sorts of infrastructure that's associated with the fossil fuel industry that takes up 1.3% of the land area. So that would be dismantled for the most part. And so the land that we would have in a clean renewable energy world is going to be less worldwide, we think, than in a fossil fuel world. So we don't think that's the problem. The next big question is, can you keep the entire grid stable? And this is a big question because, and the thing that most people are concerned about. Well, we took our 143 countries and we divided them into 24 world regions, and we did grid stability analyses where we saw if we could, can we match electric power demand with supply and storage every 30 seconds for 3 years. And when I say electric power demand, everything has been electrified in a wind, water, solar world, so except for some heat. But so we actually looked at all the electricity demand plus the heat demand together, and we found that we can match power demand with supply and storage everywhere in the world over 3 years at a 30-second resolution. And this shows the results for the United States. The top is for the entire 3 years for the whole US. And the bottom is just a 100-day period where you can kind of see the matching the supply and the demand a little better. But you might ask, well, what was the cost of this? Okay, so this is where we analyzed the cost in each of the 24 world regions that we examined. And well, the capital cost of the entire system to keep everything stable is $73 trillion. And that sounds like a lot, but keep in mind the energy industry, worldwide energy expenses are on the order of $3 to $5 trillion. Right now, the capital infusion is $3 to $5 trillion per year. So it's it's on the order of 10-15-year payback time to transition the entire world. In the U.S., the cost is $7.8 trillion. So that's the cost of a U.S. Green New Deal, and the $73 trillion is the cost of a worldwide Green New Deal. And keep in mind, the U.S. government just allocated like $2 trillion for the COVID pandemic, and that would be 1/4 of the whole U.S. Green New Deal. In China, it's 16.6 trillion because they have higher energy demand. Europe, 6.2 trillion. But on the right, the graph just shows for each region what's the resulting levelized cost of energy, which is the top number on the left. Like the world average is 9 cents a kilowatt hour. So, but how does that compare? How does the cost compare with fossil fuels? So here's on the world scale. In 2050, the cost of all energy from fossil fuels is expected to be about 17.7 trillion per year. That's like how much people spend on transportation fuels, heating and cooling fuels, electricity fuels, and industrial fuels, etc. right now it's on the order of 12 trillion a year is just what people spend on energy, and expected to go up to about 17.7 trillion. But there's another cost, which is the health cost associated with the fossil fuel emissions. And the 7 million people who die every year from air pollution, that's $30 trillion per year in 2050, brought back to today's dollars. And then the climate cost is expected to be about $28 trillion per year. So the total, which we call the social cost, or the energy plus health plus climate cost, is $76 trillion per year, versus wind, water, solar, which has no health cost, no climate cost. It only has an energy cost. It's 6.8 trillion per year. And how do you get that? How do you get much lower cost for wind, water, solar? Well, the main reason is, remember, the 57% lower demand for energy. You have 57% less energy required in a wind, water, solar world. And then there's another 10% reduction due to the cost per unit energy. Like the cents per kilowatt hour, it's about 10% lower, but 57% less energy requirements. And so you get a total of about 61.4% energy cost. That's the reduction of energy cost to 61.4%, and the social cost reduction of 91%, 76 trillion versus 6.8 trillion. So this is good news. In other words, the Green New Deal in the US would cost 6.8 trillion, worldwide would cost 6.8 trillion per year. In the US, it's about $770 billion per year. And so, and it reduces costs. There's a net huge benefit for going to the Green New Deal in the US and worldwide. Okay, so let's look last at some policies and what's needed. There are now laws in 61 countries to go to 100% renewable electricity. These are listed here. These are mostly smaller countries, or some are islands. But at least there are laws in place, and each of them has a different deadline. Most of them are 2050, but some are 2035, some are 2040. So this is good news, although we need all energy, not just electricity. In the US, there have been 8 proposed either resolutions or bills at the federal level to go to 100% clean renewable energy for either all energy or electricity. And these are listed here starting back in 2015. So the Green New Deal, which are both resolutions, not bills, they were proposed most recently, but those are only the 7th and 8th resolutions or laws that have been proposed. And they are, none of these have been voted on. So that is, even though these have been proposed, they haven't been voted on. And so they really have gone nowhere at the federal level. However, at the state level, there's a different story. There are actually 14 states or territories, or the District of Columbia, that have laws or executive orders to go to 100% renewables. Rhode Island has a law to go to 100% by 2030. Washington D.C. by 2032. Connecticut by 2040. Hawaii, California, New Mexico, Washington State, New York by 2045, and the rest by 2050. So these are actually enforceable laws or executive orders that really, and there is a transition going on in most of these places. In California, for example, we're actually already in 2020, we're at 55% wind, water, solar for the whole state. So that's really good news. I think we'll actually get to about 85, 90% by 2030, rather than the 2030 goal in California is 70%, but I think we'll be much further. Now, not to be outdone, there are 176 US cities and counties that have committed to 100% renewables, including many large cities, and those are the ones in blue. And this is really important because we need, we need city commitments, we need state commitments, we need, and local commitments, individual people commitments. If we look at another factor that's really helped the transition that's going on right now is that there are 235 international companies that have committed to 100% renewables. And they are building wind farms and solar farms in order to power their own operations. And this is really driving the large-scale change that's going on worldwide. Now, this list of 235 companies includes 8 out of the 10 biggest companies in the world, which are the ones in blue. And so these companies represent much more than 50% of all the wealth of all the companies in the world. So that is really good news. And a lot of this change has been driven not only by the energy plans that we've been developing over the last 11 years in particular, For states, we've developed plans for all 50 US states, for 53 towns and cities in North America, for 143 countries. But there are also over 100 nonprofits that have committed to moving either the US or the world to 100% clean renewable energy. And so it's these nonprofits that really get people on the ground, and really, like the Sierra Club, for example, has been very helpful going to cities and getting them to sign up and make commitments to get votes from city councils. So without all the people, this wouldn't have been done. And so we really need, it's really this change, this large scale movement to 100% renewable energy. It requires really cooperation among not only scientists and policymakers and cultural leaders and community leaders, and also nonprofits and people on the ground actually driving this change. So it's really a collaboration among multiple people and groups that has gotten us this far. Okay, so if I were to summarize, I didn't talk about jobs yet, so I'll just say one thing briefly about that. We calculated how many jobs would be created and lost from a transition in each of the countries that we looked at. And worldwide, we calculate that we'd create 28 million more jobs than are lost. And in the US, about 3 million more jobs than are lost. And these are long-term, full-time jobs. So that's one of the other benefits of such a transition. So besides the job creation, we find that the land use would be modest, 0.65% of world land area for such a transition, and most of that spacing between wind turbines that can be used for multiple purposes. We'd avoid 7 million air pollution deaths per year. We would slow global warming and then ultimately reverse it. We think we can keep the grid stable throughout the world with 100%. We would reduce energy costs by 60% and social costs, which are energy plus health plus climate costs, by 90% compared with fossil. And then finally, I just want to highlight a few additional resources. There is a course, there's a three module course that's available at the top link here at Stanford University. I'm actually now teaching a new class that is a full class that will be available publicly. It's online as well. It's not quite yet available, but it will be available publicly soon. If you're interested, but right now what's available is this three module online course. The second link is to papers, pretty much all the roadmap papers we've developed so far on our 143 country world plans, as well as state plans and city plans. They can be found at the second link. The third link are, if you want to locate kind of a summary of each plan for each country, each city, each state, you can go to the solution. Information. You can follow me on Twitter, where I provide daily updates for the most part on energy-related topics. So thank you very much, and next I'll look at questions and try to answer some of the questions that have
Mark, so you have. So first of all, if you go back to the previous slide, I was about to ask the same question. Somebody was asking if the red and blue color have a meaning.
No, they don't. They have no meaning.
Okay. Okay, other than that, so under the QA, you really have only one question, but under the chat, you have 5 or 6. So you want to read them or you want to pick them?
Yeah, actually, I'm looking at QA and it looks like I have 4, or is there one question? Okay. Okay, here's a question. I mentioned vehicles such as cars, buses, ships, and planes. What about trains, locomotives? Mainly heavy haul freight. What are the trends for the switch from diesel to electric? Well, for trains, we would also, depending, some can be electric, especially if you have induction charging on the tracks themselves. And certainly in cities, like local trains can be electric, but for long distance, hydrogen fuel cell is the other option. And that's actually, some hydrogen fuel cell trains are being built right now. And for heavy haul freight, it'd probably be hydrogen fuel cell. But you can always add more. Nice thing about a train is you can add just another car containing batteries, which is not necessarily efficient, but it's not that hard to do. So that's, I think it's still in flux about whether electric versus hydrogen fuel cell will dominate with trains.
Please go in the chat, because people have been asking questions there way back into your presentation. Can you see them?
Yeah, hold on a second. Or I did see them. Hold on. Oh, there we go. Oh, there's lots of questions. Okay. See. I see. It says saying semi-electric makes it sound like it's part electric. Well, what it was is that it's a semi and it's electric. So yeah, these big trucks are referred to as semis, but they are either fully electric in one case or hydrogen fuel cell in the other case. What are the efficiencies of energy conversion in these various storage schemes? Well, like in the gravitational storage, I think they were claiming like 82% efficiency, which is similar to pumped hydroelectric power. But like the district heating system, like the underground thermal energy storage of the boreholes, it's actually the seasonal storage efficiency is only about 58% efficient. However, that doesn't really matter because it's so cheap that it's less than $1 a kilowatt hour that you can afford to waste a lot of energy. It's not really wasting it. It's just when you're storing heat between a whole 6 months, I mean, you're going to lose energy. But so actually 58% is pretty efficient considering how long you're storing it for. But it's obviously much less efficient than, let's say, a battery, which is on the order of 90-something%. Another question, what were the political and economic factors within the university allowed these big investments in renewables to happen? It was driven by the utilities division. There's some people in the utilities like Joe Stagner and other people who were really, well, they knew a lot about, they were really interested in trying to experiment with different new technologies, and they just made proposals to the university, and the university slowly over time agreed to it. And then they came up with a larger scale plan. So it was really a combination of factors that the technologies were coming down in cost. They wanted to experiment. They had already experimented in some energy technologies that worked. Then they set some interim goals that they wanted to reduce energy use. So it was a long process, but it was partly willpower, partly having people who were interested in moving this forward. I think that helped a lot to have people who were really interested in moving it forward. And then, then they got students involved too, and the students were really excited, and they helped drive it forward as well. If other people in your neighborhood have to pay more for energy from the community choice, why would they choose that system over cheaper PG&E? Well, it's actually not, PG&E is not cheaper. It's virtually the same price for the community choice aggregation utility as PG&E. And even with 100% renewable. So the nice thing with community choice is you can actually, even if you have none of your own solar, you can actually opt into buying 100% renewable energy, electricity from the community choice. And you can't do that from PG&E. But the price of the 100% option, let's say for Silicon Valley Clean Energy, it's virtually identical to PG&E's price for dirtier energy. So it's not more expensive, even though you might think it is. But so there's no drawback, and then plus you do have options. You can pick pretty much the same option as PG&E if you want, as well. So which conditions should a region city have to make it economically feasible and maybe efficient to use residential PV? Well, right now, okay, for new buildings, like California requires everybody effectively to have PV on their buildings, unless there's like no sunshine, because they have this law that every building has to have zero net energy. But so you'd want to have, I mean, I think from my point of view, it's because of the social cost. I'm very big on looking at social costs in addition to the energy costs. because social costs really reflect improvements in your health and your neighborhood's health, and also the larger scale health, as well as improving the climate. So we really should be looking at everything in terms of social cost. And when you look at things in terms of social cost, everything is cheaper when you go to renewables. There's no issue whatsoever. Now, to make it economically feasible, it is economically feasible already to transition, given with existing, there are existing federal tax credits, and there are, in California in particular, there are state credits for transitioning to renewables. But as I showed, you will basically pay the system off, even if there are no tax credits or ever, you'll pay it off in 10 years and they're warranted for 25 years. So that means it's free energy after 10 years. Now, right now, with the tax credits, it's free energy after 5 years. So it's really, you're basically spending more money by not transitioning. And that even would apply in some cases to retrofitting as well. Retrofitting, if you have a system, there's more of a trade-off, but certainly for new buildings, you want to go to renewables. What do you make of that with
Mark? Mark, I can't hear you. Mark? We lost Mark again. Mark? Mark?
Hello?
Mark, okay. Start again at the answer to the question about Jevons paradox. We missed you there.
Says, what do you make of Jevons paradox that a more efficient energy system is associated with demand increases, not reductions? I don't, well, that's true to some extent, but I think it's also, you'll also find that it's cheaper for people when you're more efficient, you're paying less, and people like that, so they don't want to increase their demands. So I don't think that will, I think it'll be true to some extent, but I actually think people would rather save money and use that money for something else. So I don't, I think there'll be some increase, but not that much.
Okay, now switch to the QA. There's a question, I'm going chronologically. There's a question by Sagar. I am a bit concerned about environmental and local impacts of extracting and processing rare earth metals. Do you see that question?
Yeah. So keep in mind that in the United States alone, there are 50,000 new oil and gas wells drilled every year. And other countries, there are a lot as well. So because fossil fuels require the continuous mining of fuels, in addition to mining of rare earths and other materials for their infrastructure. So in our system, we're eliminating the continuous mining of fuels. We only have the mining for the infrastructure. So that's like, if the infrastructure has to be replaced, let's say once every 25 years, it's like one-time mining in 25 years for these rare earths, versus not only that one-time mining with the fossil fuel industry, but you have the continuous mining forever, the 50,000 new oil and gas wells every year, let's say in the US alone, forever. So it's an orders of magnitude less mining than the current system. It's my thoughts are that we want to, as we transition to 100% renewables, the mining process will be 100% renewable as well. So there will be no fossil fuel use during mining. There will still be mining, and so that will be invasive in the earth, but it's like much less invasion than we currently do with fossil fuels. So you always want to make things better, but we should be very happy that we're reducing mining by orders of magnitude.
And then can you take Sylvia's question, do social costs include the fossil subsidies and so on? You see it?
They can't, yeah, I see, do social costs includes fossil?
Mark, we lost your voice. Mark? 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 Hello, Mark, can you hear me? Mark?
For fossil fuels.
Mark, you have to start again. We didn't hear the answer.
So the social costs, our social costs did not include the costs of the subsidies for fossil fuels. They included the health cost and climate costs of fossil fuels, but not the subsidy cost. But to be fair, we also did not include the subsidies to renewable energies as well. So yeah, that would be an additional cost of both fossil fuels, but also some for renewables.
but we were looking at the unsubsidized costs. So to be more clear, yeah, all our cost numbers were unsubsidized costs of energy and unsubsidized social costs. Okay, next question, it looks like, does your report include embodied energy in the production and manufacturing of materials? Yes, it includes all the energy that's used for industry to produce everything, to run everything, and yeah, so it does include embodied energy. What do you think is the one remaining barrier to convince fossil fuel companies to abandon fossil fuels? Is it just irrational at this point? Can they not admit that they are wrong and they're responsible for the climate emergency? Well, I think the barrier is, as long as they're making money, they're going to continue doing what they're doing. So the key is to try to penalize them, to try to drive up their costs, to reduce their demand. So the more we transition to renewables, the less people drive fossil fuel cars and less oil demand there will be. So some of them will go out of business. Even though anyway, there's a lot of things going on there, but I think, yeah, we need policies put in place to drive down the use of fossil fuels. That's why these laws to go to 100% renewables will really push fossil fuels down. You need these command and control laws. But in addition, individuals can change themselves. If you go, your next car is electric, your next water heater is a heat pump, your next heating system and cooling system is heat pump systems. You replace your stoves with induction stoves, you replace all your light bulbs with LEDs. You reduce the demand for the fossil fuels. I think so. Individuals can do things, and policymakers can do things. Okay, so next questions. Let's see, looking at the chat.
Yeah, you should go to the chat, and there's still a few questions there. I'm trying to go chronologically, but some are just comments. From Joe 746, what are the main material and pollution concerns with 100%? You see that one?
Looking through this to see here.
746. And then we'll pick one last one because it's almost 8 p.m.
Okay.
Well, are you in the chat?
Yeah, do these plans and laws have teeth, or are they just performative in some cases? So the laws that I pointed out, the state laws and executive orders, they do have teeth. They are requirements by the state to go toward 100% renewable electricity and to 100%. And the city laws are more, they also have teeth in theory, but it's more, I think it's less teeth than the state laws. They're certainly binding, but they could be changed in the future by another city council, or they could be delayed, and they're not, some of them are just, they have deadlines that are 2050. Keep in mind, we really need a 80% transition by 2030 and 100% by 2050. And we need 80% by 2030 to avoid 1.5 degree global warming and to eliminate most of these air pollution deaths that are occurring today. And by the way, in the US, there are about 78,000 air pollution deaths per year. Worldwide, as I mentioned, 7 million. So we want 80% by 2030, and that requires a rapid transition. Now, the city laws, as I mentioned, some will have teeth, but there are a lot of them are not till 2050. And that's, so that means that they can just push it off to.
Mark, no sound. Mark, no sound. Mark, you still there, Mark?
In fact,
Mark?
If you go to the road, yes?
We lost the second part of the answer, but I think the first part was good enough.
Well, yeah, let me just mention that all those graphs and the stability graphs are available at that roadmaps webpage that you can see right now, hopefully.
Yes.
The second link.
Yes.
And then next question, what are the main materials and pollution concerns with 100% wind, water, solar? Well, materials, so we looked at neodymium, which is used in permanent magnets for wind turbine generators. We looked at platinum, which is used in fuel cells. like with platinum, we don't need any more catalytic converters, right? Because we're getting rid of fossil fuel cars, and platinum is used in catalytic converters. So we're basically moving the platinum from catalytic converters to hydrogen fuel cells. And so that would, that's like a wash. Neodymium, we have about 7 times more neodymium than we need to transition most of the world.
We lost the voice again. Mark, no sound. Mark?
So,
okay, it's back.
So, yeah, so here's another question. What, in your opinion, what are the main risks and challenges to the success of a transition? I think the challenges are, it's a social and political battle rather than technical or economic. It's really trying to get laws and policies put in place effectively and easily. And so there are people who are going to be against it. And I think that's the biggest obstacle. Because if everybody were on board, this would actually be a very straightforward, easy thing to do. But the nice thing is that it's so cheap right now to go to renewables that, in fact, like in April, 100% of all the new electricity generation in the US was wind and water and solar. And although in previous months there was some gas, so it's really only gas right now is competing with wind, water, and solar. So the next question was, well, the next question is, when are people going to start listening to our plans that we developed first in 2009? Well, they are starting to listen at the state levels. Some states, as I mentioned, city levels, businesses are listening. And I think, a lot of people want it if the public is listening, but it's really, there are obstacles in the way. And so there are still groups that are against all this. And they, when you hear like anybody talk about the Green New Deal, you always hear some counterpoint where they say it's so expensive, it'll bankrupt the country or bankrupt the world too. So there's a lot of that misinformation that has to be countered. And I think that's there's this doubt that's put in the public, this uncertainty. And so that's really what we're facing to try to reduce. We're trying to reduce that uncertainty by providing people with better information. And slides, yeah, for these particular slides, I can make these available. If anybody wants to send me an email, I'm just at jacobson@stanford.edu, the ON. And I have been, yeah. Looks like, yeah, I think I got to the end. I probably skipped a few questions, but I'm going to stop there unless there's.
Okay, no, sounds good. Sounds good. They have your email address, so they can send you more questions by email.
Yeah.
Mark, I want you to remain online because I want to decide what to do with the recording. Everybody else, thank you very much. Thank you for listening. I hope it was. It gave you the answers you were looking for. And the next one will be on June 15 with Andrea Key on robots and pandemics. And it will be a mix of a slide presentation and conversation. So I hope to see you on June 15. Go to lasertalks.com or to the Stanford calendar events. Thank you and good night, everybody. Mark.